for the refrigerator door locking. This is Rocky Jr., Rick Harrison, Rudy Diaz, and I'm Michael Florio, the team that I'm going to hand it over to Rudy to get us started.
So our goal was to design a system that lets the user when the refrigerator door has been left open and attended for a certain period of time. The device must be compact, low power consumption, and efficient. Some of the reasons for this device is that refrigerators operating efficiently when the doors are left open. This device can help reduce e-waste as well as possible food contamination. So this is a visual of how the system works. While the user is in range of the motion, no alarm should buzz. If the user leaves the range of motion, a countdown timer will start. If the user does not return to the range of motion, before the countdown ends, the alarm will buzz. In order to complete this design, we have to follow a couple of customized requirements. The first requirement is that our custom PCB had to be designed in Eagle. Our device should operate with batteries and have battery life of about 3 months or more. The microcontroller to be used must belong to the ARM Cortex family. The device should acknowledge when the user is in range and buzz alarm if the user leaves and the time is down. And for the final product, we should have a custom interface circuit for lighting motion.
Okay, so for our engineering requirements, basically what we just did was we had to split up our customers' requirements into smaller, more manageable, but specific enough chunks so that we can kind of begin to think about what we needed to do. Some of the requirements didn't really get split into a bunch of different parts, but other ones, especially the 4th and 5th requirements, definitely had to. So, talking about constraints and standards, so our biggest constraint, of course, was using our battery power, using 2 AA's. We had to make sure that it had an acceptable battery life of at least 3 months. So a lot of the work that we did was just ensuring that we could keep a low power design. We had to also design a PCB in Eagle, and our main goal at first was to just make sure that its general board size was around the size of a credit card. And normally for the microcontroller, we would have suggested using the Atmel Atmega 328P, just because of how familiar it is to all of us. But a main requirement was to use a Cortex-based controller, so we had to go with that. And the whole way through as well, we always had to consider that the fact that this is going into a refrigerator, so we had to consider relatively low temperature environments for everything. Standards, everything's written in C using Atmel Studio. All of our firmware loading was done using SWD. And for making the board, everything's done in Eagle. It uses all of Eagle's conventions. And so for ordering the board, we also used Oshpark. So we used all of their design rules for manufacturing with Eagle. But all of our other standards were pretty lax. So for the functional overview, this is just a basic block diagram of how the system works. In the top left, we have just a symbol for our interior light sensing system. This is a fully custom system that's being explained by Raki later. Essentially, what this boils down to is it detects light from the refrigerator, or I guess ambient light. And when it detects light, it will enable both the microcontroller and the buzzer using a bipolar junction transistor, or BJT. And all of the rest of the actual inputs to the microcontroller is just the motion sensor for actual digital I/O. The microcontroller, of course, is in charge of running all the timers and checking the motion sensor to see if it's going, to see if the motion sensor is detecting anything. And it'll be running the timer. If the timer runs out, it will signal the buzzer in hardware. This is just our basic program flow. Again, essentially, that's what it does, what I just mentioned. What this basically boils down to in software is that our system is pulling our motion sensor 1,000 times a second, just for pretty high accuracy, even though that's kind of overkill. But for high accuracy, and to make sure that we're not getting any false positives, so like the motion sensor sensing something and then not, and the microcontroller just not picking up on that. We just wanted to prevent that, so that's why it's polling so quickly. When it does detect any motion, it'll signal the controller and it'll reset the timer, but only if the buzzer is not already sounding. So, like I said, we made a PCB in Eagle. We made a couple of different versions for this. Our first version includes everything on board, including the microcontroller, and all of that related circuitry. And this design is roughly 1.8 by 1.5 inches, so well within the size of a credit card. We also wanted to make sure that we can just make a board that can interface a general development board, so we also made a much smaller breakout board that just includes our basic electronics, like the light sensor, and then all of the necessary connections to power and the microcontroller itself. We had a couple of issues just regarding the PCB in general at the very last minute, and that is why we actually didn't have an Eagle PCB to present, like to confidently present. But Raku's going to cover what we did to take care of that.
For our design, we considered a lot of different alternatives, different options that we had at our disposal. First of which being how we were going to supply power to the actual device. We considered either using a 9-volt battery or 2 AA batteries in series. Originally, we thought that the 9-volt battery would provide a much simpler design without any problems, but after some looking, the 2 AA's provided a correct voltage with a good amount of battery life, so that's what we went with. In the same vein, we had to consider how to save power in the circuit. So we considered either using the sleep mode and wake up functions on the chip itself, programming those to try and make the device turn off when not, or low power while not in use. And the other option was to just have a hardware-based turn off so that if there was no light and the fridge was closed, it would shut down most of the circuit completely. We ended up going with the hardware-based one simply because it was a lot easier for us to implement, and it ended up saving a lot of power for the whole design. For light sensing, we considered either using an amplified photodiode IC or creating our own custom light sensing circuit. We ended up creating our own simply because it gave us more flexibility and let us meet our requirements a lot easier. For this custom circuit, we had to consider either using a light-dependent resistor or a photodiode. We chose the photodiode because of its low power consumption and the fact that battery life was a large requirement that we had to meet. Here is our schematic for our final technical design of the circuit. On the left here shows our light sensing circuit. We used an operational amplifier to create a comparator circuit so that the output of the light detector would only be either high or low, whether it was detecting light or not. On the right, we have a transistor connected to both our microcontroller and buzzer, as well as the output of the comparator circuit, so that the entire system, when not detecting light, will shut off most of the high power draw components, saving us a lot of power and preserving battery life immensely. We also, like everyone else, went through a lot of tests to make sure that all of our designs and pieces worked. We ended up dividing ours into several different groups just so we could test multiple requirements at the same time, being a lot easier. The groups were considering the actual board itself, size and things like that, the battery life, which we had to calculate out, will be covered later. We made sure that the timer reset properly, and we had to test that the motion detection, that the range was what it said on the data sheet keeping it accurate. We also measured the sound pressure level, just the volume of the buzzer, again, to make sure it met the data sheet and our requirements. And finally, we had to make sure that the light sensor kept the circuit working properly the way it was supposed to. The only major issue that we really ran into across this was we were unable to use an Eagle-designed custom PCB for our final product. We simply ran into problems later on in the development, and we had to make use with the perf board. But the perf board represents how the Eagle design would have been, and it works exactly as we were hoping. I'm going to hand it off to Mike to talk about the power saving.
Okay, for the all-important battery life. So we accounted for this device being on about 15 minutes per day, and the alarm sounding about 14 minutes per day. So we took our current measurements, and we measured it at 346 microamps with the system off, with no light activation. With the light, 5 milliamps, light and alarm sounding 6.62 milliamps. The calculations came out to 4.5 months. That's accounting for a battery rating of 2,000 milliamp hours. And in fact, there are battery ratings higher than that, 2,500, depending on what battery the customer would buy. For the blended schedule. So the takeaway from this is we were highly optimistic the first semester. And so we anticipated even building and beginning to test the prototype that semester. Here's what we actually achieved. So we didn't quite get to the coding and building the prototype, fully assembled the prototype on the breadboard. Semester 2, the takeaway from this is we underestimated some hours and certain other hours we were spot on. But what we did underestimate was the design of the PCB and troubleshooting, just like most of the other teams designed the PCB. So here's what we anticipated, about 136 hours, and we totaled about 277. The summary and lessons learned, I broke this into 3 sections. The project alone, engineering, documentation, and then group teamwork, engineering team. For the project, all the subsystems worked properly. We had consultation with the PCB design. The hardware sleep mode was effective with the transistor. We achieved the battery life for 3+ months. We learned some troubleshooting, how long it takes. Engineering, we learned to take the customer requirements and translate them to engineering requirements, test plans, VCRMs. And as far as the engineering team, the biggest takeaway is to listen to all ideas. So the transistor idea came later in the project. Someone came up with that, and we all embraced it. We took it, ran with it, tried it, and it wasn't as simple as just working the first time. We had to run a few different wiring configurations for it to finally work. And it did, I'm glad to say. From that, we'd like to show you the demonstration. And the system is active since the light detection circuit is sensing light. We'll close the door. And the system turns off since light is no longer detected. We'll open the door, and the motion sensor detects motion, so no alarm will sound. Once we step away, the system is set for about 10 seconds. And the alarm sounds. The alarm remains sounding even when motion is detected. Shuts off once it detects no more light. The system shuts off. Back up again.
System once again turns on. Close it.
Once the refrigerator door is shut, the system turns off once again.
The timer for the system can be reset. Can be set to different times using just by recoding the forward that we use.
The light sensitivity can also be adjusted with the use of this potentiometer as well.
And that's our refrigerator door alarm project. Okay. Any questions?